I would like to welcome you to my presentation about uncertainty estimation in landmark localization based on Gaussian heat maps. Landmark localization is an important task in medical image analysis, for example for segmentation, registration or diagnosis, like analyzing defective positions in these lateral cephalograms. Unfortunately, a frequent problem in landmark localization is the often ambiguous ground truth location of landmarks, especially when they are not on distinct structures like here on the chin. There is not the correct location of the landmark, but many locations can be considered correct. Thus, the landmark prediction should not only be a single coordinate, but a distribution of possible landmark locations. Note that although from only one ground truth location per image a distribution cannot be observed, however, when looking at more images from the dataset, the distribution can be observed and estimated quite well. We perform landmark localization with heatmap regression using CNNs. In heatmap regression, the target landmarks are not represented as coordinates, but as images of Gaussian heat maps, which are learned with NL2 loss. However, a problem of heatmap regression is always the choice of the size of the target heat maps, which often does not represent the actual target landmark distribution. So we want that the network not only predicts larger heat maps for more uncertain landmarks and smaller heat maps for more certain landmarks, but we also want the predicted heat maps to be oriented in the direction of the possible uncertainties. Thus, in our work, we propose to learn the anisotropic shape of the Gaussian target heat maps for each landmark independently via backpropagation. During training, for each landmark, both predicted and target heat map receive feedback from each other. So while the network parameters are updated to better model the shape of the target heat map, at the same time the shape parameters of the target heat map are updated to better model the shape of the predicted heat map. After training the CNN to predict the heat maps, the question is how to go from heat maps to landmark coordinates. Other methods typically only take the maximum of the heat map response as the predicted coordinate. However, this does only represent one possible coordinate, but not the distribution of possible landmark coordinates. Thus, we propose to fit Gaussian functions to the heat maps to really represent the whole distribution of landmark coordinates. We evaluated our method by a cross-validation on two publicly available datasets, one of cephalograms and one of radiographs of left hands. In our paper, we have shown that our method delivers state-of-the-art performance in terms of point errors, while our best method uses both anisotropic Gaussians for target and fitted heat maps. For detailed results, please refer to our paper. Finally, I will show you some results for two example landmarks. The image on the left shows the input image cropped around the target position. The image in the middle shows the predicted heat map and the fitted Gaussian parameters in blue, while the image on the right shows the target heat map with the learned parameters. The images show that the predicted heat map and fitted Gaussians represent the landmark distributions quite well for this example. Here we show two plots of the fitted Gaussian parameters for all images in the dataset in blue in the middle, as well as the ground truth prediction offsets for all images in red on the right hand side. When looking at those two plots, we can see that the fitted Gaussians model the expected distribution of landmark offsets not only in the size, but also in the direction, thus representing a distribution of possible landmark locations. Finally, as in the dataset of lateral cephalograms, each image is annotated by a junior and a senior radiologist. We also evaluate whether the predicted landmark distributions correlate with the inter-observer variabilities. Here we show the same plots as before, but with additional senior ground truth to prediction offsets in orange and junior ground truth to prediction offsets in green. These offsets show that our predicted distributions model well the inter-observer variability too. To conclude, we have shown that CNNs using heatmap regression may be used for predicting location uncertainties. By learning Gaussian parameters of the target heat maps and fitting Gaussian functions to the predicted heat maps, our method is able to predict distributions of possible landmark locations. By showing state-of-the-art performance in two datasets, the predicted landmark distributions correlate with the landmark localization error as well as inter-observer variabilities.